In this example, we're looking at a system which is made up of this lightweight or massless bar, OA. Got two particles of mass, A and B, having the same mass, uppercase M. And this bar is pinned to ground at O. In addition to that, we have a particle P, which is coming in with some known speed. We know the direction of travel. Its line of action includes A. When it hits A, it sticks. And what we want to do is find the angular velocity of the bar immediately after the completion of the impact. Okay, so what I suggest that we do here is look at a free body diagram here of B, of A, and P. Let's put all these together. So our system includes all of this. The reason for putting all this together is that we have that impact force of P on A. And if we bring everything together, that impact force becomes internal, because the same force on P is the same as A, and it cancels out. So we look at the forces that are acting on there. Well, there's a reaction force up here at O. We've got OX and OY. And I think we're allowed to say that the dimensions of A is small enough such that once P hits A, it's virtually at the same place as A. So we don't have any moments due to weights. So this weight force of P here, that distance there is small. We can neglect that. The point being on this is that from our FBD, we make the conclusion, we draw the conclusion that summation of moments about O for the system as a whole is 0, which says that the angular momentum for the system before H1 is equal to the angular momentum of the system H2. So we just need to write down each one. But keep in mind, we are looking at the system A, B, and P. So when we write down H, we got to include A, B, and P. Well, initially A and B are at rest, so they have no velocity. The only thing we have here is the particle P. So this is R P with respect to O. It's got to be referenced back to O. Comes the velocity of P initially. So let me resolve things out in terms of X and Y. The R vector from O to P is going to be equal to a minus LJ. Again, it's going from O to P. The velocity vector for P1 is going to be VP1. And let me call this angle theta 1 so I don't have to write down a number. Sine theta in I, and then VP1 cosine theta 1 J. So again, R cross MV, we write down R and V in terms of X and Y. One thing we see here is that J cross J, that's a 0. All that's left here is the J cross I, which is a minus K, and a minus sign there in front makes it a plus M L VP1 sine theta 1 in the K. How about H2? Once impact occurs, then we have not only P, but we also have A and B. So it's going to be mass of A, the position from O to A, cross with the velocity for A. Do the same thing for B, R, O to B, cross with the velocity vector for B, and then for P. Like that. So again, the system is made up of A, B, and P. We need to write the contributions to H from all three. What do we know about the kinematics here? Well, we know that the bar is going to rotate about O. B is on the same rigid body, is on a rigid body which rotates about O. So velocity B after impact is going to be in the x. Velocity of A is also going to be in x. And same way for P, because P sticks to A. VP and VA are the same thing. Okay, so I'm going to write this still term by term here. O to A is going to be a minus LJ. The velocity of A, we know it's in the x, and since it's rotating about O, its velocity is going to be L times the omega for the bar in the I. Do the same thing for B. Its position vector from O to B is going to be minus L over 2J. Velocity of B, it's rotating about O, so its distance back to O is L over 2. Omega, it's moving in the I. And then for P, its mass is lowercase m. It's stuck to A, so its position vector is the same as A, and its velocity is the same. So VP2 is equal to VA2. That's the key point here, because it sticks. So I carry through all my cross products here. J cross I again is a minus K, so this ends up being an M L squared omega that's coming from A. I have an M L over 2 squared omega from B, and then for P it's a lowercase m L squared omega. This is all in the K. So this in the end is going to be what, 5 force m plus lowercase m times L squared omega K. We argued above that H1 is equal to H2, so I said take that, set it equal to that, and I get that M L VP1 sine theta 1 is equal to 5 force big M plus small m L squared omega 2. I guess that's for time 2, so I should put the subscript there. And therefore, in order to find omega 2, I take M L VP1 sine theta 1 and divide by 5 force m plus m L squared like this. So this is the rotation rate of that bar after impact. What did we do? Well, the first step was to choose the system. The system that I chose was A, B, and P all together. And the reason for this is that there's a lot of forces, interactions going on there, but if we make that system as a whole, those forces of interaction are all internal. The only forces acting from the outside are the weights, and they effectively act through O. The reaction force at OX and OY act through O. So the key thing here was that the moments about O are 0, angular momentum is a constant. That is the important step. Here just writing out H initially, only P moves, so it's R cross MV for P. After impact, A, B, and P all move, so we have to write down R cross MV for each one of those, add them up, and basically just remember that when P hits A, it sticks, so whatever A does, P does. Velocity of A, that's L over 2 times omega. Velocity of speed of A is L times omega. Substitute all that in there, use our conservation of angular momentum, and we get the angular speed of the bar after impact.